Hi everyone, this is the second video for Thursday's lecture, which is covering key basic concepts in NLP that we'll need to delve into more detail next week to talk about the transformer and transformer language models. And so this video is about models of words. All right, so specifically, I'm going to introduce static word representations. What I mean by a static representation is that the representation of the word is the same regardless of the context it is used in. And so river bank versus money bank, bank would have the same representation. So you would almost always want to use contextualized representations in your research. However, we're covering this material because it's important background for understanding the development of NLP and kind of the differences between what we use now and what was used more traditionally. You may see it used in papers, and there's a few contexts where having a static representation may actually be a feature more than a bug, and we'll see one example of that at the end of this lecture. All right. So I want to start by saying just a brief word about traditional models of words and what this looked like in the pre-deep learning era. And so the traditional approach was to use a data set like WordNet, which is effectively a thesaurus containing lists of synonyms and hypernyms. So this was made by humans with these human-engineered relationships. And the problem was that required a lot of human labor to create and maintain. And also it could lack nuance or comprehensiveness. It didn't exist at all for lower resource languages. And it was static and just very costly to create and kind of limited in its nuance. All right. And so you can imagine treating words as discrete objects and just encoding them with one-hot vectors, where the vector dimension is the number of words in the vocabulary. So why would you not actually want to do this? First of all, there's no notion of similarity with one-hot vectors. By definition, they are orthogonal. Moreover, suppose you have 500,000 words in the vocabulary and you want to encode a thesaurus using one-hot vectors. That's a 500,000 by 500,000 matrix. And so obviously it's going to create computational problems. One-hot encodings of words are not really a computable objects. So how else can we represent words such that they are computable? Well, kind of in any course about NLP you take, you'll see this obligatory quote from the 1950s, "You shall know a word by the company it keeps." And what this is saying is that if you can explain the correct context in which to use the word, then you understand the meaning of that word. And so this leads us to the concept of a word embedding, which is a dense vector representation of a word. And by dense vector, I mean that in contrast to the kind of the one-hot vectors, which are sparse vectors, dense vectors have values in their positions rather than being mostly zeros. So words are embedded such that words that appear in similar contexts have similar word vectors, and words that appear in different contexts have more different word vectors. Okay, and so to compute word vectors in the pre-deep learning era, count-based methods predominated, much as we saw count-based methods predominated in NLP more generally in the pre-deep learning era in the one of the other videos for this lecture. And so the idea was to consider words in their contexts. Contexts are the words that appear in a nearby window. And count-based methods, also known as distributional models, created a word context matrix that counted the number of co-occurrences between words and the surrounding words in its context. So this was a really large matrix, and so they did dimensionality reduction with singular value decomposition. And in practice, they needed a lot of hacks to make this work. In other words, remember the objective with a word embedding is that words that have similar meanings should have, or that are used in similar contexts should have similar word vector representations. And so to get this count-based approach to work, you had to log the frequencies and ignore common words and weight the windows and do a whole bunch of other things. But once you did all of these hacks, you got something that looked kind of mostly reasonable. And I'm citing a paper from 2005 that's sort of the seminal paper on these pre-deep learning methods. All right, so now I want to jump to Word2Vec and see how Word2Vec created these word embeddings, where again, remember the goal is that words that are used in similar contexts should have similar representations. And so what Word2Vec does is to create non-contextualized representations. So I hate this movie. There's a representation for hate and for this and for movie. Whereas a contextualized representation would jointly embed the entire input sentence and then create representations for each word that depend on its context. So that is what the transformer does. We're going to see contextualized representations next week, but in this lecture we're talking about non-contextualized representations. Words are embedded separately, and so the representation for the word is going to be the same if you're using the same model, regardless of the context in which that word is used. All right. And so the objective function of Word2Vec is shown here. And so for each position, we want to predict the context words within a window of fixed size M around a center word, which we'll call WJ. And so we want to minimize negative log likelihood. And the question is, how are we going to calculate the probability of the context words given the center words? And so in Word2Vec, we're going to use two vectors per word. We have VW when the word is the center word, and UW when the word is the context word. And we'll take the dot product of those two vectors, which compares the similarity between them. So if we have O and C, their dot product computes their similarity. A larger dot product implies more similarity, which in the context of word vectors, remember, means a higher probability that those words are used together. And we can normalize this over the entire vocabulary to get a probability distribution. So recall from earlier in the class that this is just an example of a softmax function. The challenge of doing that in this context is calculating the denominator of the softmax requires computing similarity with every word in a potentially very large vocabulary, and it's infeasible to do that for every step in training. And so instead, you can do something called negative sampling. So create positive samples, which are words that appear in the context, and negative samples, which are words sampled at random from the vocabulary. And what this effectively does is create a logistic regression model where you've replaced softmax loss with a sigmoid that predicts whether the words are neighbors or not. And so our goal is to move word vectors around so they're good at predicting what words occur in the context of other words. And that means we maximize the objective by assigning similar embeddings to words that tend to be used in the same context. So let me give a visual representation of this, and it might help it to make more sense. This is taken from Jay Alamar's blog. I also recommend checking it out. He's really the master of explaining things with these amazing visual posts. So if we want to train Word2Vec, we create a matrix for embeddings for the target word and a matrix for embeddings for the context. And so each of these, the dimensionality of this is the vocabulary size by the embedding size. Our embeddings can be, that's a choice. I think in Word2Vec, they were typically something like 300 dimensional vectors. And so at the start of training, this can be randomly initialized. By the way, I think they trained Word2Vec on Wikipedia, just for some background. Wikipedia's great because it's all open and it's a lot of text. You might find it useful for your own research as well. So at each training step, take a positive example and sample some negative examples. And so in the example given in this post, the sentence is something like, thou shalt not do something. And then the randomly sampled words from the vocabulary are Aaron and taco. And so the input word is not, and thou is an actual positive word that appears in context, so its target is 1. And Aaron and taco are the randomly negative sampled words. Remember, we're sampling negative words at random because we can't compute the softmax loss over every word in the vocabulary because that's too costly to do, but we can just take negative examples. And so we look up the input word in the embedding matrix, and what you see there in green, and the context words in the context matrix. And remember, we have every word kind of in the vocabulary in every matrix. So we've looked up those embeddings, and then we're going to take the dot product of the embedding vector with each of the context vectors. And remember that the more the higher the dot product, the more similar those two vectors are. And the resulting number measures the similarity of those two vectors. Okay, pass it through the sigmoid. Okay, and then compute the error and use that to update the model parameters. And now we move on to the next positive sample and its negative samples, and so on and so forth. There's a variant of this called continuous bag of words, where you predict center words based on the sum of surrounding embeddings. Okay, and so people were extremely excited about word2vec. Word embeddings have some pretty remarkable properties. So this is kind of a famous example from the paper where you see, man, and you add some amount, you add some vector to it and you get woman. And then the same thing that you add to uncle gives you aunt, or to king gives you queen. And so this is an example of analogies, which I think is the thing that people got the most excited about using word2vec for. And so people use these on analogy tests. And so there's a package that will let you compute these analogies. So Australia is to beer, as France is to champagne, good is to fantastic, as bad is to terrible, and so on. I mean, I don't know quite how cherry-picked these examples are, but in general, you can get analogies that at least some of the time seems to make a lot of sense. In high-dimensional vector space, a word can be close to lots of other words in many different directions. So you can potentially capture many dimensions of similarity. The window size for the context you want depends on what relationships that you hope to capture. So small windows are good for indicating words are interchangeable. Smaller windows will tend to extract more syntax-based information, whereas larger windows allow context to have a larger effects. And embeddings are more likely to measure similarity in terms of the relatedness of words. And I've cited a toolkit here. All right, so how would we think about evaluating how we're doing? That can be hard to think about in an unsupervised task like word embeddings, as there's not really a clear evaluation metric. And so people thought about intrinsic evaluation, how good based on the features produced, or extrinsic evaluation, like how useful for downstream tasks. And so one approach that you saw taken was dimensionality reduction. I think, as I said, I think word vectors were something like 300 dimensions, reduce it to a much lower space and see if it looks sensible. You can correlate word vector distances with human judgments. There were data sets collected by psychologists on this. So there's this WordSim 353 data set that was used a lot in this literature. And you see that in the first column here. People also evaluated performance with analogy data sets. And And then finally, there was categorization tasks, which were human-created data sets with 4 words, which of these words is not like the other, which will sound familiar to anybody who watched much Sesame Street growing up. All right. I want to say like a final few words on word vectors and thinking about interpreting them. And so this is another kind of example of how word vectors can have meaning from another version called glove, which we didn't have a chance to cover here, but you might see it used if you delve too much into this literature. And so, yeah, the one key thing is that we didn't optimize the model to do well on analogy tasks or on the Sesame Street task or any other task that it was evaluated on. We tried to do a simple task, which is to predict words in context using unsupervised methods. And the word vectors with these powerful properties were a side effect of this. And this is going to be a theme in NLP, that good representations can have kind of very powerful properties and can be useful for tasks that you want to do, even though the model was not pre-trained to do that specific task. So, you know, I think I already said in the last video, if you learn only one thing from this course, okay, so I'll say if you learn only 2 things from this course, a second thing that I would like you to learn is that neural networks can learn better ways to represent data than what humans can engineer by hand. And that theme should become abundantly clear. Representing data well is essential to downstream tasks that we want to perform. All right. And so this relates to another kind of really, really important thing that's going to show up over and over again in this course, which is the power of transfer learning. So the general approach of learning a good representation for task 1 and then using it to perform a downstream task 2 is called transfer learning. And that's just going to be a very powerful theme in this course. And so we'll see that ImageNet pre-trained backbones estimated on a data set of natural images, some large share of which are different types of dog breeds with pretty limited fine-tuning, can be a powerful features extractor for working with documents. Transfer learning is very prominent in NLP as well. And word embeddings powered a bunch of other things that were done with NLP kind of in the mid-2010s before the transformer really took off. All right, so we often initialize a downstream NLP task with embeddings and then fine-tune the model to extract the relevant dimensions from those embeddings. And this is going to be the norm in most economic applications. Another kind of separate but relevant note that I wanted to make here was about some work that was done on bilingual word embeddings, because this is going to be a precursor to some of the things that we see, especially when we go to talk about multimodal learning. And so this figure is shown from a paper that aimed to learn to embed words from 2 different languages into a single shared space. So taking words from English and words from Mandarin, and you train 2 word embeddings, but you optimize such that words that we know are good translations are close. And kind of the striking thing about this paper is that this did reasonably well on words not exposed to during training, which I think is just a really interesting point, that's suggesting somehow that human languages have similar topologies, such that when some words are forced to align, other words align as well. All right, so nothing about this says we can only embed data of the same mode into a single representation. One could, for example, classify images by producing a word embedding vector. So when you show an image of a dog, the model should be close to the word embedding for dog, and similarly for cats or whatever else. And so what's really remarkable is what happens when you test the model on a new class of image. Within a fully supervised image classifier, this would be a problem, but we'll actually see kind of multimodal models that think about doing zero-shot or few-shot image classification by mapping language and images into the same space. Okay, and the final note I wanted to make was from a 2016 paper that I believe was in PNAS, and you'll see it on the reading list. It's using word embeddings on this historical corpus of American English, which is like mostly books that are in the public domain, to look at essentially at biases in the corpus. And so, for example, it's looking at vectors that are very similar to she relative to he, that represent different occupations. And so you can see things like, homemaker, nurse, receptionist, librarian, socialite, etc. They also look at gender stereotypes and she-he analogies when the word embedding model is trained on this corpus. And you can definitely see stereotypes there. And so then they look at it by decade. So top adjectives associated with woman in 1910, 1950, and 1990 by the relative difference between the embeddings of those words, again, trained on this historical corpus of sort of public domain books by decade. And they argue that this can be used to approximate shifts in gender stereotypes, at least if you think this corpus is representative. And again, you see these very strong these are adjectives that are strongly, used in very, very similar contexts to she, but not to he. And they also do something similar to look at Asian stereotypes, which I believe that they do by looking at the most common names of Chinese descent versus common white names. And again, you see some pretty extreme stereotypes. So I thought this paper was a really interesting example of using word embeddings to look at things that economists would find inherently interesting. All right, and that is it for word embeddings. So now there's going to be one final lecture for Thursday on sequence to sequence. Thank you.